Good afternoon, everybody. It's too loud? No, it's okay. Okay. So I'm going to speak about tertiary treatment. I would like to give you a few examples. But I think, well, I'm not sure, but let's try. I would like to be more or less quick. I will give you a brief introduction because I've not been here in during the whole summer school. But I'm not sure if you have, somebody have spoken to you about the problem, the frame of why we are working on what we are working on. So I always trying to start explaining you how I think is in my opinion, the most important problem nowadays because of the climate change. So I will speak a little bit about the OPs as tertiary treatment also, and of course the case studies focused on water decontamination, but also in water disinfection for reusing purposes, okay? So I think nowadays all of you, I hope, agree with the first sentence of this slide. So world population evolution is at the roof of most serious human problems. So one of the most worrying problems nowadays worldwide is the water scarcity. And it is expected to become even worse in the coming years due to the huge increase in population. Here you can observe more or less that in 2050 we are going to be more or less 9 billion people in the world. So imagine the amount of water we need, not only for drinking, we'll see after, also for food, for producing food and for producing energy. So there are a lot of maps like this regarding water scarcity, which is imbalance between availability and demand of water. It is important to have some numbers to have a general picture of the problem and trying to focus the problem to focus the application of solar advanced oxidation processes technologies and the application. So for instance, by 2025, 1,800 million people will be living in countries or regions with absolute water scarcity. And 2/3 of the world population could be under stress conditions. So let's focus a little bit why we are working in this field. And it's of course because we are going to need an alternative water source for continue having more or less the same quality of life that we have now. And of course, thanks to the quite advanced analytical tools that Professor Anawera told this morning, I'm sure, we have observed that there are a lot of compounds that are now present and now being detected in a very, very low concentration between micrograms and nanograms per liter. They are known as contaminants of emerging concern, and they come normally from industry, hospitals, houses, agriculture. They go to the sewage. They are normally in the outlet of the municipal wastewater treatment plant, and they are also in rivers, in superficial waters. So as soon as we want to recover this water for other uses, we are going to have this problem inside, and it's a problem. But we have also not only chemicals, but also we have water pathogens, water microbial contamination. We have bacteria, viruses, protozoa, fungi, but we have also what we know now, antibiotic-resistant bacteria and antibiotic-resistant genes. What's that? We are abusing of antibiotics. I'm sure you know that. And so we have bacteria that are getting used to that. They modify their genes and they are resistant to the antibiotics. This is why the pharmaceutical companies are in the fourth generation of antibiotics now, because we need new antibiotics each time. So we have to try to eliminate this or inactivate this also in the water if we want to reuse that. And I suppose you know also that the highest consumption of fresh water in the world is in agriculture. 70% of the fresh water in the world is used in agriculture. And of course, it's quite clear that we need water not only for drinking, because we maybe use like 2 for 4 liters. I only drink maybe 1 liter per day, if I'm lucky. But for producing food, we need something like 2,000 to 5,000 liters of water. But we need also water to produce energy. And there are a lot of people that don't know that. Here, we have here the example of Almeria. Well, that doesn't work. This is our zone, the southeast of Spain, Almeria, and we have a very big area of intensive agriculture. So we have a very high requirement of water for that. So that's the problem. I haven't said anything new to you, I hope. No? Okay. I don't know, you heard something like this in the school before? You heard about the problem before? I suppose, okay. So regarding the AOPs, I'm not going to go into this because, of course, it has been widely explained. Basically, we are producing hydroxyl radicals. Of course, I must stress the importance of using those that can be powered by solar energy because we have an added value. Of course, the sustainable part and the green chemistry could be inside. But there is something quite important. When we are dealing with real wastewaters, we have a lot of complex matter inside. We have a lot of things that are not known. But we have a lot of ions. We have not only, we have chloride, we have sulfate, we have a lot of things that can modify the behavior of our treatment. So we must be aware of that because we are always speaking about the hydroxyl radical, but there are other oxidants that are not so powerful as hydroxyl radicals, but are quite longer in lifetime, let's say. So they can stay longer in the mixture, in the wastewater while you are doing the treatment, so it could be beneficial. Indeed, Dr. Ricardo told us about that, having sulfate radicals or also chloride radicals, so it's quite important also. Don't focus only in hydroxyl radicals. What about, let's say we must work with real wastewater as soon as we can, because the treatment you want to apply never is going to behave the same in the still water, on tap water, on the real wastewater. So it's important you focus your problem and try to work with the real water as soon as possible. Of course, if you are starting a process, you need to know how to behave your process. So of course, maybe you are going to start with the still water, but you can start with a little bit more complex water and try to complicate little by little to see how it behaves. What happens with photophantom process, for instance, all of us, we know that it's the optimum pH is 3. And of course, if we are dealing with real wastewater coming from the outlet of a municipal wastewater treatment plant, it's not logic to reduce the pH and then afterwards, for the reusing purpose, increase it again. So they say that the new investigation on this is trying to work at neutral pH, but for that we need to maintain iron in solution because at high pH it precipitates. So we use iron complexes to trap the iron, EDDS, citric acid. Indeed, we have seen that there are a lot of advantages apart of maintaining iron in solution, because we have seen that it absorbs in the UV visible region and can form additional oxidative species that can help in the treatment. So I'm going to drink a little bit. What about the reactors? I know that, I think all of you have seen that the most used reactors for advanced oxidation processes are compound parallel collectors. And you know perfectly the advantages, so I'm not going in there. But when we are dealing with the tertiary treatment and when we want to eliminate only the small concentration of contaminants that we have inside of the water pathogens, there are other options. And Professor José Antonio Sánchez already told us, because they are working on that, and we collaborate with him and with the group of the SOL. And of course, there is the option of raceway point reactors, because what we need is a very low amount of energy, very low treatment times to eliminate this concentration of contaminants and to inactivate the pathogens. So why, with the CPC, then we have problems on limitations of the absorption of photons and other things that I think Professor José Antonio already explained us. So this is another good option for this kind of waters. So as you see, we have a very broad spectra of options for testing, but we have to try to focus on which of the treatments are good, or let's say are fit for us for treating and for testing for our problem, or for what we want to do, for the objective we want to attain. So if we want to reuse the water coming out from the urban treatment plant for irrigation, then maybe it's enough if we eliminate 80 or 90% of the contaminants and we inactivate pathogens, and for that, the amount of energy or the treatment time is very low. So I will show you now examples. So just as an example, this is an example of the amount of contaminants that we can have and we can measure in the outlet of a municipal wastewater treatment plant. As you can see here, we have the sum of all of it's quite low in nanograms per liter, and we have a lot of amount of contaminants. Of course, you will see, okay, when I would like to work with real wastewaters, but I don't have the necessary equipment to follow that, because we need a chromatography coupled with mass spectrometry, as Professor Anahuera told us. But we can do a lot of things quite near to the real conditions, and I will show you examples that not always are done with this high quality and analytical equipment. We can do a lot of things with lower concentrations, but not so low that we need that equipment. We can do it in an HPLC, normal HPLC. I'm not going to show you quite the last results we have, because I think it's better to try to well, not to teach you, because I'm not a professor, but trying to show you from the beginning how we have been going on these kind of things. Of course, we started working with, well, not the still water, but mainly natural water, or tap water. And we started working, okay, we want to work with neutral pH, of course. We don't want to work a pH acid if it's possible. But then in that case, we observe problems with the bicarbonates. Of course, the behavior of the, for instance, photophantom process for the elimination of these are the contaminants in this case. Of course, the elimination of the contaminants is not so good in the solar photophantom process when we are in a natural water with bicarbonates, because the carbonate also trapped the hydroxy radicals. So now we have the first problem with real waters. But if we try to reduce the pH, but just with the intention to eliminate the IC, the carbonates and bicarbonates, then we will have a better performance. And this is the kind of things you wouldn't see with the still water. These are just to show you at least the pilot plants that we have and that we're using. We are speaking about solar photophantom in the CPC, or solar photocatalysis in the CPC. But we want also to compare what is commercial, what is ozonation, also like ultraviolet as tertiary treatment. Of course, you can take advantage of ozonation and also use increasing pH or adding hydrogen peroxide to have also hydroxy radicals and to convert it in an AOP. But at least compare with something that is commercially available. So one of the things we started doing is, okay, classically, let's see what's the difference for the elimination of contaminants of emerging concern in an effluent of a municipal wastewater treatment plant with solar heterogeneous photocatalysis, titanium dioxide, and with solar photophantom here at acid pH. Because we were starting. What we saw clearly, just what Professor José Antonio said, we had something like a saturation in the solar titanium dioxide photocatalysis in the tubes. So we need higher path length. And indeed, we had a very high treatment time or illumination time in this case compared to solar photophantom, of course, at acid pH. So it's clear it's going to be better. We compare with ozonation, which is a commercial one, and we try to go With this objective, the 98% of elimination of the contaminants, let's try to compare and to do an economic assessment. Because this is another thing. We cannot compare only by comparing efficiency from the technical point of view. We need to compare also from the economic point of view and the life cycle assessment possible also, just to decide which is the best treatment. And in this case, for us, it was quite surprised that solar photophantom and ozonation were comparable, mainly because of the energy cost in the ozonation process. And one of the things that happens when you are applying tertiary treatment in the field and you apply ozonation is that, let's say, people apply ozonation and generates a lot of ozone, so the energetic cost is even higher because they don't optimize the dose that you actually need. So that's another problem. What is the other option? Following what Dr. Vitor told us about the combination, of course, always the best option is trying to combine to reduce costs and to improve the efficiency. And when we say combine, there is an option in the case of tertiary treatment of, for the elimination of contaminants in the effluent of a municipal wastewater treatment plant. It's trying to concentrate those contaminants to reduce the volume to be treated finally and to increase the concentration. So the concentration of reagents in your treatment technology will be also reduced. So maybe you can reduce the costs. So the idea, for instance, in this case, is to have, you can check the direct treatment, the direct tertiary treatment of the outlet of the municipal wastewater treatment plant by the solar photophantom process and try to do it at neutral pH, or you can try to combine with a nanofiltration system to concentrate the effluent, to increase the concentration of contaminants, and to reduce the volume. So you reduce the total volume that you are going to use. And then go to the solar photophantom process, for instance, or ozonation or whatever, just compare several of them, to finally eliminate the contaminants. Here we have, this is the example of the municipal wastewater treatment plant. These are all the contaminants that we measured, and also what was the concentration, how it changed the concentration between the direct effluent and the concentrated one. So of course it increased. So if we compare, we did both. We did at pH 3, which is the classical photophantom, from the direct effluent and the concentrated effluent, with the aim of attaining the 90% of elimination of all the contaminants. And we went to the pH, neutral pH, by using the complexing agent EDDS. So we want the same option. We more or less had the same energy. We consume more hydrogen peroxide, but we have a higher TOC, a higher total organic carbon coming from the EDDS, but we attain the same at neutral pH. So important here, again, costs. And check if it is worthy or not to do it in the concentrated stream. Of course, we do not reduce a lot, but it's important already. So important always to do economic and life cycle assessment if it is possible. This is another AOP that can be applied. This for solar photoelectrophantom, but electrooxidation also. So this is done by Irene. She has been already asking things. So one of the things you have done is trying to simulate the nanofiltration membrane concentrate before doing it with real wastewater, but it is a simulation with more or less the same concentration that we can find in the outlet of the nanofiltration system when you introduce the effluent of the municipal wastewater treatment plant. And let's see what's happening in the anodic oxidation. And in this case, it's more or less the same system as Dr. Vitor explained, BBD and the anode and the cathode. In the anode, we have the generation of hydroxyl radicals, but we have the generation of another radicals if they are inside the system. So if we have chloride and we have sulfate, they are going to be produced also. In the cathode, we produce online hydrogen peroxide. So if we add iron, we will have solar photoelectrophantom if we also combine with the compound parabolic collector. So the important thing here is to see, we have to add also EDDS if we want to maintain neutral pH and not to lose iron maybe. But we have observed that only with anodic oxidation, results were not so bad for 2 of the contaminants. The contaminants are here, terbutrin, chlorphenbinphos, pentachlorophenol, and dichlorphenac. If we go to the solar photoelectrophenol, that's it, anodic plus the cathodic, so we have photoelectrophenol and solar, we have better performance with similar energy consumption. In the case, if we take into account the sum of contaminants and we try to attain the 90% of elimination of the sum of contaminants, we have better performance, slight better performance with the solar photoelectrophenol system, 80% removal. Of course, we have there some other disadvantages because we have to take into account the cost of DDS, cost of the electric generation of these radicals. But what we want to do with this water after the treatment is to reuse it. And of course, in our case, to reuse it in agriculture and crops irrigation. So one of the tests that we did, and Immaculada also did in collaboration with Luigi, and it was like the application of sunlight and hydrogen peroxide at very low concentrations for the elimination of the inactivation of pathogens and also antibiotic-resistant bacteria in the combination with contaminants at 100 micrograms per liter, so it's quite low concentration, just only with sunlight and hydrogen peroxide. And of course, trying to reuse the wastewater in crops irrigation, in this case, with lettuce. And it was done real experiments in our camera, crop camera, which is this one, trying to see how these contaminants, how this treatment behaves and let us to irrigate crops without any problem, let's say because of the permanence of maybe some pathogen or maybe some contaminant. Regarding pathogens and antibiotic-resistant bacteria, it was antibiotic-resistant bacteria E. coli in fecalis. It was clear that in activation the limit of detection was attained, so we can be happy that we are not going to have those when we irrigate in water. But sunlight with iron peroxide is not so efficient, of course, for contaminants. So we have only the elimination of flumecine, but carbamazepine and thiabenazole were here both. So what happened when we irrigate the lettuce and what happened with the leaves and soil when we irrigate several weeks with this water? So this was done also in collaboration with the CESOL, with Anahuera. And so we have R1 and R2. R1 is when we did the treatment, the hydrogen peroxide and solar energy, 5 hours. R2 only 90 minutes. But what we see, and it's clear, this is in leaves, and this is in the soil. So what we have clear is as soon as we continue irrigation week by week, we have an accumulation of the 2 contaminants that were not eliminated. So they are there. Other thing is that when we are speaking on reusing this wastewater for crops irrigation, then we have also to speak in health risk assessment and how they could affect when we eat these crops, these products. So this is another thing that must be done also. If you need to do life cycle assessment and economic assessment for choosing the best technology when you want to treat or to eliminate contaminants and pathogens, you have also to apply health risk assessment when you want to reuse this wastewater for crops irrigation. I'm the quickest, for sure. So some key message for, I think this is a general view, at least for more or less the group. So of course, water scarcity and bad water quality is a real problem affecting all the world, not only those zones of the world that are in, I don't know, in South Africa or in the south of Spain, or no, this is something affecting the whole planet. Also the countries in the north of Europe. So it's a real problem. And we have to be aware of that. Of course, municipal wastewater treatment, so that the wastewater, the effluent treated, plus desalination, both together could be another solution or another source of water for reusing purposes. So that's important. Of course, as I've been speaking about that the whole presentation, but we have to do a deep evaluation of our problem. What is our objective? What we want to eliminate in the water, and in which activity we want to reuse the water. Of course, there are different advanced oxidation processes technologies, and normally they all show a high efficiency for the elimination not only of contaminants and antibiotic-resistant bacteria genes, those of them that are energetically powered, let's say solar photophotone ozonation, those of them normally are quite efficient, but this is not the important thing. For selection, you must take into account economic and life cycle assessment always. And the last one is coming from Inma, and I fully agree with her. Advanced analysis of treated wastewater as well as contaminant transfer to crops must be carried out for ensuring a safe reuse always. So we fully agree on that. This is the group. I think more or less you all of us know to us. Leo is here, like in. And thank you very much for your attention.